Hello. In the last part we have discussed about accounting method, and we see the example of stack operations and how this accounting method was used in that stack operation to perform the amortized analysis, right? In this part we are going to explore the binary counter example, and we are going to perform the amortized analysis using the accounting method on this binary counter. So what is binary counter? If you can remember from the previous lecture, so you can remember that the running time or the time complexity of the binary counter was dependent on the number of bits that are going to be flipped, right? Because the while loop was iterated. I mean, at the order of number of bits flipped, right? So how we are going to assign the amortized cost, okay, in this example. So what we are going to do, we are going to assign a cost of 2 when we are setting a bit from 0 to 1. Okay, so that cost, if you try to understand that whenever we are setting a bit from 0 to 1, it is going to take in actual one cost, right? So one cost will be used for paying the actual cost of setting a bit, and another cost will be stored as a credit, okay, and will be used in future when we are resetting the bit, okay. So here for each bit we are having we may have some credit, okay. So whenever we are setting that bit from 0 to 1, we are having one credit for that bit, so that which can be used in future to make it from 1 to 0 again, okay. So obviously resetting a bit, that is making it from 1 to 0, will have no cost, okay. uh, so this is the two amortized cost that is assigned to setting a bit and resetting a bit. Now if you can remember, I mean, this amortized cost has to be assigned to the operations, right, of the counter. So here this setting a bit and resetting a bit is not the operations, okay. Now we have assigned this amortized cost over here, and from that we are going to derive what will be the amortized cost for the increment operation, okay. So if I ask you what will be the amortized cost for the increment operation, so if you try to remember, so let me show you the algorithm. So this was the algorithm, right? So what the algorithm is doing, so in the while loop it is basically checking if any bit is 1, okay, from the right side or from the LSB, so it is making it 0, right? And once it get out of the loop, it is checking if it is in the range, then it is basically making the ith bit from 0 to 1, right? Now if you look at the setting, I mean, cost for setting a bit and resetting a bit, you will find that what we are doing over in this loop, we are basically making in this loop we are basically making all the bits from 1 to 0, right? So here we are making all the bits, I mean ith bit, from 1 to 0. So whatever we are doing over here is basically taking 0 amortized cost, right? Because setting resetting a bit from 1 to 0 is taking no amortized cost, right? So this loop, how much time, how many time it is going to be iterated, it is going to be take 0 amortized cost, okay. And over here it is going to take 2 amortized costs, right? Because in this statement we are basically setting a bit from 0 to 1, right? So if you look at the increment operation, so what is the amortized cost of this increment operation? So as per this definition, you can see that the amortized cost for increment operation is only these two, right? Only 2, and there is no amortized cost that has been incurred by this loop over here, okay. So the amortized cost of increment operation is only 2, because only one set operation is occurring in the increment, that is only one bit is going to converted from 0 to 1, right? And rest of the bit in that operation is converting from 1 to 0, okay. So that's why the amortized cost of this increment operation is 2, okay, which is equivalent to setting a bit. Now again the question comes that is the assignment of this cost is valid? So you have to consider again that whether the credit is always non-negative during the sequence of n operations. So if you try to understand what will be the credit, so initially we will have suppose for a 3 bit, let us consider only 3 bit, okay, 3 or 4 bit, okay. So initially we will have all the bits as 0, so all the I mean initially we have 0 cost, okay. So this is non-negative. Now initially whenever they are 0, what you can do, we can make, I mean you can make it 1, right? Any bit over here you can make it 1. So as soon as you make it 1, the cost is going to be no, I mean the credit is going to be 1, right? Because if you one credit, one cost is going to be used for paying the actual cost, and one is going to be for the credit, okay. So credit is going to be 1. So you can understand that any of the bit, okay, over here can be either 0 or 1, or in other terms there will be no non-negative number of ones, okay. So since there is no non-negative number of ones, this credit can always be positive, okay, either 0 or positive, okay. So the credit is always non-negative during the sequence of n operations, okay. Now the question comes, that is the total amortized cost an upper bound of the total actual cost? So let us see with the example whether the total amortized cost is an upper bound for total actual cost, okay. So I have made this table for you for understanding. So we have the same 5-bit counter over here, okay. We have the same 5-bit counter over here, and the counter is basically changing the values or incrementing the value upon each increment call, okay. So this is how it is done. Now what we are considering, we are basically considering what is the actual cost, okay. So initially there is no actual cost, right? Now actual cost is depend on the number of bit flipped, right? So in the next operation we have 1 bit flip, right? So this 0 becomes 1, right? So the actual cost is 1 over here for this operation. Now again, if we do the increment call, how many bits are flipped? This one is flipped, this one is flipped, right? So the actual cost for this operation is 2, okay. Now again, if the increment operation is called, what will happen? This bit is flipped only, right? There are no other flip, so actual cost is 1. Now again, the increment operation is called, this bit is flipped, this bit is flipped, and this bit is flipped, right? So the actual cost is 3, okay. Like that all the actual costs is given over there, okay. Now what will be the amortized cost for each of this increment operation, okay, sequence of n increments operation. So initially the amortized cost is 0, and we have found that for each increment operation the amortized cost is 2, right? So every time the increment operation is called, okay, the amortized cost is going to be 2, right? So every time we have the same amortized cost of 2 for each of the increment operations. Now what was the condition? The condition was the total actual cost has to be upper bounded by the total amortized cost, okay. Now let us see what is the total actual cost after each increment operation, okay. So initially total cost was 0. Now after the first call, okay, first call the actual cost is 1, okay. So this 0 plus this 1 is is your new total actual cost, okay, which is 1. In the next operation we have actual cost of 2, right? So previously we have actual cost of 1, which will be added to this new actual cost, okay. So the total will be, total actual cost after this increment call will be 3, right? Now in the next increment call we have actual cost of 1, so that will be added to this 3 and we'll have actual cost of 4, okay. Now in the next increment call we will have actual cost of 3, so that will be added to the total actual cost to find to have the new actual cost, I mean new total actual cost at that level is 7, okay. So in this way the actual cost column is added to the total actual cost to find out the total actual cost after each increment operation, okay. Similarly we can find in the same way the total amortized cost. So initially it is 0, next the amortized cost of 2 will be added to that 0 to find out the total amortized cost to be 2. Next step again it is taking the amortized cost of 2, so it will be added to this 2 as 4. So you can understand that this is going to be, I mean incremented by 2 in each step, because all the amortized cost for the increment operation is 2, right? So this total amortized cost after each iteration, I mean each increment call, is going to be increased by 2 from 0 to 2 to 4, then 6, then 8, then 10, like that, okay. Now you have to check that whether this total amortized cost in each step is having, I mean, after each call is having an upper bound to the total actual cost. So you can see that this 0 is equals to this 0, or this is less than equals to this, right? Total actual cost. Next we have total actual cost 1 and total amortized cost is 2. So again we can tell that total actual cost is upper bounded by total amortized cost. Again we have 3 in the total actual cost and total amortized cost is 4, so it will be less than equals to 4, right? Again 4 is less than equals to 6, 7 is less than equals to 8. All the way, I mean, if you check that in all the cases the total actual cost is basically having less than or equals to value as compared to the total amortized cost. Okay, so then we can tell that total amortized cost is basically giving an upper bound to all the cases. Okay, hence the amortized cost that we have assigned to the increment operation, which is 2, is a valid amortized cost because it is always non-negative and it is also giving the total actual cost. I mean, the total amortized cost is upper bounding the total actual cost. Okay, therefore we can tell that the amortized cost of the increment operation is nothing but 2, which is again order of 1. Okay, so we have, in the last slide we have seen that the amortized cost of increment operation was 2, which is nothing but order of 1, right? 2 is nothing but order of 1. So the increment operation has an amortized cost of order of 1. Okay, so this is how we perform the accounting method on the binary counter example. Okay, so in the next part we are going to see the potential method, and see you in the next part.